Hi, I'm Shane McGrath. Today, I'd like to talk about digital signal processing. So previously, I've mentioned about kind of transformers and how they could be used for software or firmware in particular. Um, However, today, I'm going to want to look more I suppose, reasoning side of transformers and how I think this relates to digital signal processing. Um, so yeah, the previous video was kind of like a throwaway video, which tried to kind of give a picture of kind of how a sinusoidal function kind of looks like every day, which is like the monthly cycle, I suppose, or even the yearly cycle, and that can kind of be viewed in a clock form as well as also the kind of each individual day, I suppose. So those sort of uh, sinusoidal waves can be compared to the attention mechanism, which is what I'm trying to do here, I suppose. And then the clock is the kind of the cycle of the attention mechanism, I suppose. However, again, I wouldn't be an expert in this space, but the book that I excerpted this from um, mentioned digital signal processing and had neural networks as part of the digital signal processing literature. However, it's not an area that I've seen relate related together, and this is coming from somebody who's a novice, I suppose, in this space. But like I said, um, uh, cool. So digital signal processing. So yeah, the traditional digital signal processors and neural networks. So yeah, the main difference between the two is that digital signal processors use kind of filters or algorithms, whereas neural networks use kind of data. So the neural networks are kind of the data kind of it defines what the algorithms are. As I said, I kind of mentioned or looked at kind of the approximation theorems previously, or approximation properties. So the data is more defining the algorithms as opposed to the engineers or the scientists. And this is kind of like uh, uh, something that is ever present for the kind of algorithms or filters that the engineers mightn't, or scientists mightn't know the specifics of the data. I mean, they kind of work as kind of these kind of gold seekers with the kind of the beepers. That image of um, they've got the kind of earpiece, and they're kind of waiting for something to beep. Um, where neural networks, it's kind of the data defines, whereas digital signal processing is a bit more scientific, I suppose, where the you're kind of you're more hypothesis based, off theory and stuff like that. Um, yeah, so the traditional digital signal processing works off convolutions and Fourier series. Uh, yeah, I said this is kind of what I would say is not the thesis, but these sorts of convolution filters is are more present in the data that than might have been previously thought, and they kind of act as digital signal processors in combination with neural networks. The data itself is almost a kind of convolution. Again, not quite an expert in the space, but that's seemingly what I would the gist is what I would say of this. And this adds to the kind of not so much the reasoning, but the kind of the signal is processed, I suppose. Um, Cool. So yeah, so how are digital signal processors different from previous types of processors? So you kind of have your microprocessors. So this would be your chips, I suppose, and then you have your like step by these kind of work in step by step logic, which is again similar to the step by step logic that no, that large language models work through. Um, uh, yeah, so I said these transformers, or not transformers, sorry, these computers work through either data manipulation or math calculation. So the example of the data manipulation would be how a computer prints. So a computer continuously tests the input device. So this is the printer and the mouse. And then for binary code, it indicates print the document. And then when it sees the verification, so this is the value testing, it moves the data from printer from the computer to the printer. So it's the data movement, and that's kind of how these not these compute most of personal computing would function. Which is different for the digital signal processing. So, digital signal processing is motion control, scientific and engineering simulations, and then addition and multiplication would be the functions of it. Um, so yeah, it's this is an example of the digital signal processing. So the parallel I'm trying to put here. As the novice, um, is um, the attention mechanism and the multiplication. So each of these kind of A0, A1, A2, A3, A4 is a kind of attention mechanism, and the MLP, the multi-layer perceptron, is kind of the addition function. Uh, Again, this is like there's a lot more going on, and this is like a very simplistic parallel, but the main point I'm trying to make here is that this kind of Fourier series wave this is the how it could be not a, it is present in the transformer. As the main point here again is that Y1 is there is a kind of mathematical function here of Y into these attention mechanisms. Um, uh, so this is the digital signal processor. So these are kind of designed to quickly carry out fear filters and similar techniques. So this is impulse reading, I suppose, and they differ from offline processing and real-time processing. So the offline processing is where the data kind of resides in the computer. So the example the writers here give is the all of the data for a seismic kind of a geophysicist, a seismic kind of reading, and then when another reading is appears, then uh, that each the new reading replaces the previous reading. Um, so this is kind of like there's a significant amount of um, time between the readings, so you wouldn't necessarily need real time processing for this. And this is kind of how most computers kind of work with presumably updating like an Excel formula would be that's how much time that would take. So real-time processing is more stuff like hearing aids, radar, where the input signal and the output signal are there's very little time between them. There might be a few milliseconds, and the circular buffer is the example of how this works. Each of these parts here are um, all each of these X's here can be seen on this sort of waveform here. Each of these would kind of be an attention mechanism, I suppose, um, which, yeah, again, this is me coming from a kind of a beginner's point of view. Uh, I could be reaching in a way, but I just wanted to highlight the parallels between and how like a computer, a transformer is. So the main difference between the kind of store values on the left and the stored values on the right is 20045. The pointer, which is the pointer, is the value for each of these. So I've done this is kind of like a computer sciencey C programming sort of stuff. So the value there is different from the value on the right. For a circular buffer, it takes less operations than a serial program would to compute these to update the sample. So from 204 to 20045 to 0046 to 0047 to 0048. So these pointers would be kind of samples from the data set, I suppose, a radar or a kind of telephone call or that sort of thing. Whereas the pointers higher up this array are kind of more to do with the instructions and the processing of uh, how the program operates, I suppose. Um, yeah, so this is kind of like the circular motion. Um, So this is how the algorithm, the circular buffer, kind of the steps it has to go through to complete that cycle. Um, Crucially, the difference between the circular buffer and the serial program is that the circular buffer, in order to change a sample, um, it has to kind of move from it only has to go from 6 to 12, whereas the serial processor has to do 1 to 14. Cool. And then these are the various different architectures of these kind of microprocessors. So the von Neumann architecture, the famous mathematician, has the most simple architecture, which is CPU to memory. So the data and the instructions, so this is the kind of coefficients for the filters, the convolutions, the program instructions. So this would be similar to the prompts and the prefixes, I suppose, those sorts of things. So once the architecture for the CPU, in order to develop it more, and the program memory and the data memory are kind of split and they kind of operate in parallel. So most DSPs are kind are similar to this sort of architecture. Uh, um, yeah, the crucial idea here is that the parts of the computation are split and they operate in parallel. And then this kind of is developed more with the super Harvard architecture with data memory, CPU, and the I/O controller. Um, cool. And then this is kind of a typical digital signal processing architecture where there's like more it's broken out even more into parallel. So crucially, the writers want to highlight how these kind of um, parallel kind of processing allows this algorithm here to kind of run at about 100 clock cycles, as opposed to so the clock cycle would be these kind of waveforms here, at around 100 time clock cycles, as opposed to about 1,000 clock cycles for the serial processing. Again, the serial processing is when kind of things have to move not in parallel, but more similar to the von Neumann architecture there. If you do look at it like that. Um, so yeah, crucially, these kind of architectures are kind of similar to LLMs, are becoming more kind of like agent-like, where parts of um, the computer is kind of split into different uh, computation architectures, and then you kind of get for the more advanced computations, you get these more advanced architectures. Okay, cool. So this is kind of so the more advanced reasoning part of the software, as I would put forward. Again, I'm kind of coming here from not too much knowledge of how the actual the LMs work on the inside. So any feedback would be fantastic. Thank you for watching.